Okay, I'm giving you one option, not two, because last time the two options diluted the vote, but I've been hearing from many of you that you really wanted to postpone, and the majority rules in this case, not half the class, majority of the class. So I don't care either date. The exam is, I already have the exam. So, and the exam, no matter what or when, is going to cover till the end of IR lecture. So, yeah.
So does that like push all the quizzes and exams back?
No, nothing will be pushed.
Opening statement, you do not want to take this exam, then go into O'Sullivan, get destroyed then. Just because you want to party.
Politics, yes, Peter.
Thank you.
O'Sullivan will destroy you. Vote the
Okay, so listen. Those of you that would like to postpone the exam 1 week, raise your hand. Oh my God. Okay, put your hand down. Without counting, it's the majority. Okay, here's the thing. Okay, listen. Okay, those of you that did not raise your hand, I understand that I don't want you to be misfortunate with that result. If you prefer to take the exam early, you're welcome to do so. Just let me know that you want to do that. Vote for me. Okay, great. All right, okay. Excitement in the air. Let's continue. Huh? Now you're pumped for atomic absorption. Okay, what's the difference between AA and AE spectroscopy? Atomic absorption versus atomic emission spectroscopy. You know this? I see hands, Sarah.
One of them measures how much light is coming off, and one measures how much light is absorbed.
Which one is which?
Emission, I think so.
Yeah. Yes.
Absorption.
Yes. So exactly, with absorption, we're measuring the absorbed light. With emission, we're measuring the emitted light, which is at a longer wavelength, less energy than the absorbed light or the absorbed energy. Okay. What's the source of excitation? Now, all of you done the AA so far and had the lecture. So what's the source of excitation in AA? Go ahead, Ted. That's with AA, so you have the excitation coming from a lamp source. What about a ICP, inductively coupled plasma atomic emission spectroscopy? It's a mouthful. I think we were, yes, Katie? Yes, well, with when the argon gas is ignited, it becomes a plasma. So the plasma is the source of atomization and source of excitation. There is no lamp. Okay. What's the type of energy absorbed during the atomic absorption process? Type of energy, or the spectrum of light. UV vis. So it can be like you did in the lab. So the iron was in the UV range and the calcium was in the visible range. Okay. Now I didn't talk about this yet, but you had it in lab. How do we get the minerals in solution, Billy? We dissolve them in strong concentrated acids. Yep. All right, so that was the last slide that we had, and I was talking about ICP. How is it different from flame emission? ICP, from the name, inductively coupled plasma. So plasma is the source of atomization and excitation, and how plasma is generated as such. Well, I will come back to this, but this would be a better figure to show that. So you have argon gas that would go through a tubing, and then you have an ignition. There is a spark. The ignition will ionize the argon gas, and then you will have ions and electrons. And then the energy source is your the copper coil that will have a radio frequency generated, and then the energy from the radio frequency is going to be transferred to the ionized gas, similar to the mechanism of the microwave energy transmission. And then when that happens, the temperature is going to rise, and you will end up having really high temperatures in the plasma. And that's how the plasma is formed. So the plasma is formed, and then you have the nebulizers similar to what you have in AA. So you do have a nebulizer where your sample is aspirated into the nebulizer that would make the solution into mist, and the mist will reach the plasma, and then volatilization occurs, atomization occurs. And then the plasma is again the source of energy, and then the atoms will be excited, and they want to go back to the ground state. They will emit energy when they are going back to the excited state, and the emitted energy is gets diffracted by a grating system and then analyzed by photomultiplier detectors. So this is a system that we call simultaneous photomultiplier system or instrument, where you have multiple photomultiplier tools, but usually you can't have more than 7 or 8 due to space in the instrument. But you can do simultaneous analysis of 8 different elements, for instance, because then each wavelength you can select for any particular element, and then you can get 8 analyzed at the same time, or the absorption of or the emission of 8 is read simultaneously. In sequential, which is phasing out, you don't see many of the sequential instruments. You would have one photomultiplier tube, and then you will just sequentially read by changing the selected wavelength of emission. Sequentially. It is still fast, but it's not as effective or as quick as when you have simultaneous detection. But still, this has its limitation. When you only can fit 8 or 7, then there are new instrumentation where you have different type of detector. Oops. The detector is a charge injection detector, and I'm not going to claim that I know how it functions, but it gives you instantaneous reading of multiple elements. This is just what I just explained. Exactly what I explained about sequential and simultaneous. Now, the initial spectrophotometer or spectrometer is the most advanced, and that allows the detection of simultaneously many elements. It functions, this system has two diffracting units. You have a prism, and then a grating system, and then another grating system, I mean here, and then the mirror that reflects all of the light, different wavelengths to the detector, and you get simultaneous reading. Again, I'm not going to go through explaining how these detectors work. It's beyond my understanding, but just know that this gives you simultaneous detection. Even the book doesn't go into that either. So, preparation of samples. So, although I didn't explain how they work, what you need to know is the initial detector allows simultaneous detection of multiple elements. So, and it is the most common detector nowadays, coupled with the ICP detection. Okay, it's definitely very expensive. So application of atomic absorption, like you did in the lab, you were determining minerals in the lab with in different food products. But in order to determine the mineral content, you need to remove carbonic matter or organic matter. So to do that, you have two types of ashing. We'll talk more about ashing when we cover the ash chapter, but how your samples were prepared by dry ashing. So we put the food product in a crucible, and the crucible was placed in a muffle furnace, and then the sample or the food product was incinerated, meaning the temperature was really high, and the carbonic matter oxidized and burned off. That's what we call dry ashing. The wet ashing is where you actually use strong acids to digest the sample. And these strong acids will result in the same outcome. All of your organic matter will be oxidized and burnt off. So you will also end up with having CO2 and O2, SO2, all gases burnt off. The advantages of wet ashing over dry ashing is you don't get high temperatures as much as in dry ashing. You do digest at a high temperature, but not 485 degrees C. So you don't get volatilization of some volatile elements.
So, for example, like in our lab, when we were doing iron and we got 50% instead of 100, would doing wet ashing would help us?
If doing wet ashing, if the reason for getting 50% is nothing to do with the actual company doing miscalculation or anything like that, it most likely, and you didn't do a dilution error, a factor of 2, then yes, most likely the dry ashing could have resulted in evaporating of iron, especially that those particular samples, it was so hard to ash the total, right, Claire? So the total was so hard to ash it, you had to re-ash it again. What they did is when they took it out the first time, it was very dark in color. The ash, that means you still have carbonic matter. So they added nitric acid, heated it a little bit, and put it back in the oven, in the muffle furnace, and then it became gray, white. So you would think you did a good job removing the carbonic matter, but in the process you might have lost the iron as well. Yeah, wet ashing, you would definitely not lose iron due to volatilization. If you have underestimation, it will be definitely due to different reasons. Direct injection can be done only when you don't have a complex matrix. For example, sometimes oil. If you want to measure minerals in oil, you can use direct injection right away. You don't have to ash the oil. So in dry ashing, you don't have any reagents up until the time you're actually solubilizing the minerals. And that's where you use HCl and lanthanum chloride, for example, for the calcium. So minimal reagent use. However, in wet ashing, there are more reagents because you're using other acids, sometimes a combination of acids. What I want to say here is reagents can be not necessarily contaminated. They may contain elements. They might contain iron. They might contain other minerals that you're interested in quantifying. So that's why we always run a blank. And the blank, like you did in the lab, you start from even the crucible. Empty crucibles are ashed as well. And you go with an empty crucible and follow the exact same procedure as you did for your sample to account for any mineral that may come from any other source than your actual sample. And that's what you did. You put the blank in the instrument, you measured the blank, and you zeroed. Okay, standards. Always for quantification, we need standards. And the way you prepare the standards, you prepare them the same way you prepare the samples. So you would use the same HCl and same type of glassware. And labware or lab classware specifically, I have it here because you can talk to Claire how she hates this AA lab because of the amount of washing they have to do and preparing and ashing and doing all the preparatory steps before you actually work. How many weeks ahead you start?
9 days ahead.
So they start preparing 9 days ahead. Yeah, so it's not necessarily the favorite lab for Claire. So they do wash because they could, these glassware and containers, they could be contaminated with minerals, but different levels of contamination. So we cannot guarantee that the utensil that you're going to use for sample rep 1 would have the same contamination as sample rep 2 or same as the blank container. So that's why everything will be washed same to ensure that everything is clean of any contaminants. Even the crucibles that are used are pre-ashed before they would put the samples in them. So it is really a tedious kind of a preparation before we can run the analysis. So calibration, you all did calibration. So we do select standards that are as pure as possible, obviously. And we want to make sure that we have a linear curve. Absorption and concentration is linear, the relationship. That's why if you noticed or if you remembered, so the iron had different concentration than the calcium because the iron linear range is more at the lower concentration than the calcium. With the calcium you went up to 20 ppm. With the iron it was barely, what, 5 ppm? Can't remember, but something smaller. So it's very important to work with the linear range, and that is done by experimentation. We have to figure out the linear range. Once we know it, then we generate our standard curve. Now, Cindy wanted me to talk about units a little bit with calculation from standard curve. So I'll do that. I know that there are a lot of confusion about if you have an equation of the line, what would be, how would you determine the units? So if you have an absorption, really there is no units for absorption, but oftentimes you see it reported as AU, absorption units. Okay, so or area, we all know that area in general has a unit, but we don't report it with the actual units of area. We can just give it an A for unit. So if you use for area A, let's say an absorption unit, absorption AU for absorption unit, then you will see how things will cancel in your equation. I'm going just to create a fake line. So I'm going to just say this is your equation of the line. So that's your absorption. This is your slope. And this is your intercept. Okay? From your algebra, slope is run over rise, right? No, rise over run from my algebra. Yeah, rise over run. So rise over run, that means AU over whatever your concentration, microgram, let's say, per ml. That's your ppm. Okay? So your absorption, let's say the absorption is 0.8. So it would be 0.8 AU, and then 1.2 AU over microgram per mil, and then you're solving for x, plus 0.05 AU, right? And then you just go 0.8 minus 0.05 AU, and then what you would do is you would divide by 1.2 AU over microgram per mil. So what happens here is your AU will cancel, this unit will go up here, and then you'll get your whatever that number is by microgram per ml. Okay. Good. Question? Okay. So interferences. There are different types of interferences that might impact the result. One is spectral interference. So iron and zinc have the best absorption or maximum absorption. I believe it's 235 nanometer. I'm not sure of the number, but they're very close. In lab, you didn't measure at that UV length. You measured at 248 point something. So in order to avoid spectral interference so that you're not measuring both iron and zinc, you select another wavelength that you think you know that you will get a measurement, an absorption. Like I said, you have previously, you have different atoms and different molecules absorb a different wavelength. We tend to use the optimum or the lambda max, but in this case, see now I have, this works, I have new battery. So in this case, the iron was measured at less than lambda max, not less, different than lambda max. Background, we talked about different sources of error. One of them was when we don't get complete atomization. That means when your flame is not hot enough. We call it cold flame or colder relatively flame. That's when your molecules don't break into singular atoms. So you will have those larger particulates in the flame that will scatter light. So less light will reach the detector and the calculation will result in higher absorption. So that is a fake high absorption. The molecules did not absorb light, they did scatter light. So in order to avoid that, we make sure that we have as much complete atomization as possible with the correct flame temperature. Transport interferences, whatever that means is the reagents. Whatever the reagents contain, particulates or other, that might result in scattering of light or absorption even of light at that wavelength. So in order to do that, your standards are prepared the same way as your samples, same way as your blank. We talked about solute volatilization in lab when basically if calcium forms phosphorus, forms a molecule with phosphorus, the calcium pyrophosphate. It's really, the bigger molecule will not get into the flame and will not volatilize into the flame. That means you won't be able to detect it. It will not be in the flame to be atomized. So that's why you guys use lanthanum chloride. Ionization, here, the opposite of a cold flame, you will get a hot flame or very hot flame that you will result in ionizing your atoms, then they will absorb at different wavelengths. You can either put ionization suppressors, or usually we just control the temperature of the flame. So if we want to compare AA to ICP, they both have the same purpose, measuring trace metal. And then they have very high precision and accuracy. If we consider the AA, the advantages are really simple. It's an older technique, so the ins and outs of it has been known for longer. And it's widely available, it's cheaper, so you'll find it quite often. But if you work at a company that does a lot of analysis, so let's say Medallion Labs or Covance Labs, they don't have AA, they have ICP. AES, because they can afford it. They can buy instruments that are expensive, and they often are managing large amount of samples, and they want to measure multiple elements in a short period of time. So that would be their choice, because you can have faster analysis and you can run multiple samples. And then you have the stability at high temperature in terms of ionization. However, detection limit, of course, you have much lower threshold with ICP compared to atomic absorption. And it's not table 24, it's chapter 9 now, 9.3, not 24.3 if you want to check in the book. Questions about AA? You guys are all expert in AA now because you've had the lecture and the lab. Okay, moving on to the best spectroscopy yet, IR.
Actually the best.
Do I ever lie to you? That's my favorite. But it does have a lot of application in industry. And can you give an example? Now that you are all working on your projects, by the way, due on the 20th, some of you have met with me already, some of you haven't heard of or from. So keep that in mind. So where do we apply IR in industry? Anybody that interned, anybody that is ahead in their project? Where do we apply IR in industry? Yes, we use it for identification. Can you give an example where in industry they would use it? Ted? So you and Walter are talking about two different things, but both are correct. You're talking about compositional analysis that is fast, quick, yes, online. Walter was talking about identification of functional groups. So, for example,
would you maybe do it if you were trying to see your concentrations of fructose versus glucose in corn syrup or something?
so this is composition. You can do that. What I think Walter aimed to say, different functional groups, but it's used in kind of forensic work. So I'm going to identify the presence of melamine really quick in my infant formula. So I'll show you an example of an IR spectra where the infant formula spectra versus a melamine contaminated spectra. So yes, functional groups and detection of molecules and quantification. So it's used for different purposes and quite used in industry. All right, so the IR region really spans from, let's see, it spans from 0.8 to hundreds, right? Infra to red, so right below red, and longer wavelength than red. And then it goes up to 100 micrometer just before the microwave radiation. So, however, in food analysis, what we really care for is the two regions within IR, the near infrared and the mid infrared. We don't care about the far infrared, we don't use it. So the far infrared is anywhere between 15 micrometer to 100 micrometer. So the near, meaning the closest to the red, 0.8 to 2.5 micrometer, then the 2.5 to 15 is your mid IR. We don't do anything with far IR. So with IR, you have different types of instrumentation. And some instrumentation use dispersive, some instrumentation disperse light, that is. So use the dispersive instruments, and we'll talk about that. Others are Fourier transform, which are really mathematical kind of, it's transformation of data. And then reflectance of light, and then transmittance of light. So we'll talk about the different types of this instrumentation, basically. You can do qualitative, where we're identifying functional groups. And an example would be detection of an unwanted contaminant, or detecting the presence of unwanted contaminant is an example. Or you can do quantitative, like measuring online the moisture or the protein that you don't want to do using longer primary methods. So applications, I was just giving you applications, but you can do qualitative detection, you can do quantitation. Under quantitation, it's for composition, but we call it secondary method. That means it's based on calibration using primary methods. And primary methods, if you remember from earlier chapters when we started, are those that are official methods of analysis or approved methods of analysis that have been validated. So always using IR for quantification and to determine, for example, composition, this would have to be after calibration using primary methods. So qualitative detection, identification by looking at trying to do structural elucidation, because absorption in the IR are very unique to the bonds or the functional groups. So if you know the spectra or the band at which certain functional groups absorb IR, you can try to figure out the structure by looking at the spectra. Because every peak or every peak that you see would be due to stretching or bending of a particular functional group, and we'll talk about that. So you can use structural elucidation to identify, and that goes under qualitative, and you can do identification and detection. So there are a lot of advantages to IR. So it is non-invasive, meaning the sample will not be destructed. So you can reuse it. Rapid, you can get analysis really quick. And the beautiful part is oftentimes you don't have to do anything with the sample. For example, you can have a wheat flour, and you put it in a sample container, and you get its entire composition. Granted, you have to calibrate the instrument. So it's suitable for routine analysis, quick online analysis, and I can't say that enough, only if it's calibrated. And then it's very energy efficient and environment friendly. So same principle as any type of absorption, you need the radiation, but in this case it's a source of IR, and it goes through the sample. And then after going through the sample, some of the constituents of the sample will absorb the IR radiation, and the remaining transmitted light will get to the detector. And then this creates a fingerprint. It creates a fingerprint because you see here there is no diffracting light, fraction of light. There is no selection of one wavelength. Everything's going to the sample. Well, there is a diffraction of light, but there is no selection of light wavelength that you would select for one absorption. So you get a fingerprint or absorption of vibrational radiation or energy at multiple wave numbers. No two structures will have the same fingerprint, which is an added plus. So just to remind you, so it is a vibrational energy. So it has to do with the vibration of the bond. So it's moving from ground state to first vibrational energy, second, third, and fourth. So there are allowable transitions. And if a molecule will absorb light only if it has the exact same allowable transition as the light that hits it. Okay. So, yep, that's basically what I said. There are atoms are in forming bonds in a molecule, and they're constantly vibrating, and the change in the vibration due to the absorbed energy is related to the functional group and even the concentration of that functional group. So what's unique about IR radiation is usually measured in terms of its frequency. So you won't see absorption by wavelength. You would see transmittance by wave number. That means the number of waves per unit time, and that's related to frequency. So that's how in IR it's different than UV vis absorption, is that you don't plot absorption over wavelength, you plot transmittance of light over number of wavelength or wavelength number. And wavelength number is basically 1 by the wavelength in centimeter. So you will have more, this number will be higher if this is lower. So if the wavelength is lower, you will have higher number of waves, obviously higher frequency, because the lower the wavelength or the shorter the wavelength, the higher the energy. So that is the unit, 1 over wavelength in centimeters. So the unit of wave number is centimeter to the negative 1. Okay. So that's some animation to illustrate stretching and bending of the bonds. And what I want you to take out of this animation is that bonds are in constant motion, but when they absorb light or IR radiation, there will be a change, an increase in their vibration. So they're not like in constant and then you give them energy and they start vibrating. They're always vibrating, but when they take on energy, there will be an increase in their vibration. Yeah, that's what I said here. So there will be a change in the amplitude of molecular vibration. And it will only vibrate, or there will be only a change in the vibration if it got the light within its allowable changes or energy changes. And what happens is, you know, the dipole moment has to do with the electron talking to each other between adjacent atoms, so that will cause a change in that momentum when it absorbs IR radiation. Okay, this is a typical mid-IR, and usually mid-IR will give you nice sharp peaks, and it's also often used for structural elucidation because it really, you get good resolution between the peaks due to being sharp, so you get distinctive functional groups identification. So this, for example, is butyraldehyde, and then there are certain groups that will absorb IR radiation at different wave numbers. So like you see here, it's percent transmittance. In percent absorption, you have positive peaks. Because it's transmittance, when the functional group absorb light, less light will be transmitted, right? So when you have zero transmission, then you will, not zero absorption, I mean you'll have 100% transmission. When you have absorption, you will see a reduction in the transmission. Okay, so that's the opposite for absorption versus wavelength. Here you have negative peaks. Okay, so the CH, saturated CH stretches, like the CH3, for example, saturated meaning they don't have double bonds, so you will have unique transmittance at a particular wave number. And for every carbonyl, you will have a specific wave number. So basically here, that's where you do structural elucidation. And here's a table that you don't have to memorize, obviously, but it does show you that in different groups, what is the absorbing functional group? Within alkanes, what do you have as can absorb the IR radiation, and at what frequency? Frequency measured by wave numbers. And same, it's just an illustration of what you can detect for each of these different compounds. So IR radiation can be employed for mineral analysis following atomic absorption technique. No bonds, thank you. So it's a common mistake, though. That's why I eventually put it as a true or false question. So this is the oldest system of mid-IR. And it's based on dispersion of light. So you do have a monochromator, you disperse the light, and you select one particular wavelength for the absorption. So its component is very similar to UV vis, and you have double beam. Double beam meaning you would have a reference cell and a sample cell, and the beam split between them. So what I want you to know out of this is that you have a radiation source, obviously a monochromator, and then a detector. That's what you need to know, not more, because this is no longer. So it started here and it went to other advanced or different systems for IR spectroscopy. One is when you hear FTIR, that's Fourier transform infrared spectroscopy. Very common, very powerful. So radiation is not dispersed. All wavelengths arrive at the detector and are measured simultaneously. Analysis is rapid. You have high signal to noise ratio. That means you have little or no significant noise. And you do a Fourier transfer time of calculations, mathematical calculations, to convert radiation into a spectra. Now, remember when I don't know if you remember, interference of light, and I said I'll describe this for the IR. So you have, instead of having a monochromator, you have an interferometer. That means the IR beam splits, and then it's recombined by different positions of mirrors to have a constructive or a destructive result. So either you get an amplification or a cancellation. The reason that they do that is to enhance the sensitivity at a particular wavelength for a particular functional group. So if you're interested in a certain functional group and you want to intensify the signal, you can use the interferometer to get more light with higher amplitude so that you get higher sensitivity. And if you want to reduce the signal from other interfering compounds or functional groups, then you can use the destructive for that particular light or wavelength. So of course the physics is complex, but I'm simplifying because this is how I understand it. Simply is you can change the amplitude to direct your sensitivity to what you're measuring. So compared to the dispersive instrument, it's faster, you get out more information, and a higher identification power. So in mid-IR, you can measure transmission or you can measure reflectance. If you measure transmission, it's usually for liquid sample because you want the light to go through and not viscous sample. Can be used for solid if it is pelleted and dispersed in an oil or with potassium bromide. But it's mostly used for liquid samples where light can be transmitted through easily. And there are different types of cell windows that can go with it. You don't have to memorize that. So reflectance, you can have attenuated total reflectance or internal reflectance. The only difference that I would like you to remember is this goes with solids that are either paste or very viscous liquid or powders. And here what happens is light does not penetrate through, it gets reflected. But what you have on the surface, whatever molecules you have in the surface will absorb some of the IR radiation and the rest of the light will be reflected, and that's what would be measured. In internal reflectance, that means here you use it with liquid samples, but it goes not only on the surface, it goes inside, or it goes, it penetrates a little bit, few micrometer, and the molecules or the compounds in your liquid will absorb IR and then reflect the rest of the light that wasn't absorbed. So it gets reflected back. Okay. So you can do a lot of different things with FTIR. It's a very powerful tool. Like I said, you can connect it with the GC to get a pure compound analyzed. So you can get the separation first. And once the compound is separated, then you can do, instead of MS, you can do IR, structure elucidation. Microscope, which is really cool, where you put the sample under the microscope and you project the beam of light onto that spot where you have it on your microscope slide, and then you get a transmittance or reflectance reading. So, of course, you can do quantitative application. Beer's law does apply, and it is used, the mid-IR specifically, used mostly to analyze milk components. So there are, they call them IR milk analyzers. So for fat, the main functional group that is used is the carbonyl group. And then the protein is the amide, and the lactose is the hydroxyl group that gets detected and measured. And they can be done simultaneously. Sample needs to be homogenized, and of course, the instrument calibrated against samples of known concentration. So in the past, when we used to have a smaller group, I would take the class to a lab where they do milk analysis, and they show us how this instrument works. It's very cool. They produce their own standards. They create milk. Within the milk, they create a standard curve for proteins, for fat, for lactose. So they change the concentration of these components in milk so that they do the calibration of that instrument. But now that there are 43 of you, we don't go there anymore. So newer mid-IR instrument that for a milk analyzer uses the FTIR principle, where you can do multi-variate regression, and then you get, because of different absorptivity at different wave numbers, you will get calculation instantly for all of the different components. I know I can hear things closing, and that means time is up. Huh? Oh, no. Okay, sorry. Just stay for a minute, Claire and Chelsea. These are not the quizzes yet. I'm still looking over them. Chelsea finished grading. I'm just looking over the quizzes. These are lab reports for the Monday group. So the Wednesday group can leave, and Monday group will get their lab report.